Hi, my name is Amelie Bond. I'm going to be talking about PigNet, structural vibration-based swine activity recognition in real farm environments. This is a collaborative work with Jesse Codling, Ganita Narutip, Yuen Dong, Wachirwit Siripangtanagong, Sipong Ariadet, Agrit Sangpet, Oratai Sangpet, Shijapan, Heyoung No, and Peijiang. So why do we want to monitor pigs in farms? That way we can help farmers and animals. By tracking animals, we can both increase the livestock welfare and then by doing that, help out farmers. We can do this by detecting events like birth, which allow farmers to save more piglets, and also track and analyze behaviors that may be more or less helpful to the animals. For tracking birth, monitoring the birth event halves the number of related deaths. So if we can detect beforehand when birth is going to happen, then we can have someone, a farmer there to monitor the birth and save piglets, especially from suffocating. After birth, sow maternal behaviors can hurt piglet survival. For example, a sow that doesn't lactate as much means the pigs can't nurse as often, and so they may starve. And a sow that lays down too often or too quickly may crush her piglets more. So if we can detect nursing, we can detect if the piglets are likely to starve, and if we can detect the sow movements, we can detect things like frequent laydown. And we can use this to determine which sows make good mothers and which don't. Some previous approaches to swine activity recognition includes manual monitoring, where people look at the piglets. But to do this, you need to have experts who know what to look for, and of course it's also labor intensive. We also have motion or pressure sensors, which can detect activity level very well, but they tend to require pretty dense deployment because they only detect where the pig is standing, or if the pig is right in front of the motion sensor, it'll detect the movement. And the pressure sensors especially can be difficult to integrate with the farm flooring. And we have wearable sensors, which can be specific to specific pigs, which is great, but they also may be damaged by the pigs because the pig farm is not a very clean or friendly environment. And then we have vision, which is very versatile. It's easy for people to look at and understand, but it does have high processing requirements and line of sight requirements. For example, piglets are often hidden by the body of the much larger sow, and then it may be hard to see what they're doing. Additionally, farmers often don't want cameras in their farms because it feels sort of more privacy invasive. So our approach is to do activity recognition with structural vibration. Pigs in a pen, they cause vibration in the structure every time they move. So if a pig steps, then that step will cause vibration in the floor, and if it rolls over, it'll cause a vibration in the floor. We can track these vibrations with sensors that we attach to the underside of the pen, as seen in the bottom picture. This is sparse compared to pressure sensors, and it's easy to integrate with the existing structure. We just tie it to the floor. The sensors are not accessible to the pigs, which means they'll last longer and be more protective. We don't have to worry about visual occlusion, and we also have low storage and bandwidth requirements. So we do have some challenges. The first one is environmental damage caused by a really challenging, messy environment. And our second one is time-varying noise in the signals. Because the farm is such a busy environment with so much going on that it's hard to tell what these sensors are recording. Is it piglet movement? Like, see in this picture we have a sensor and it's detecting the nursing activity of the pig. But then when we have the environment, we have changes in the vibration caused by weather, caused by the temperature, caused by a worker cleaning the pen. That makes it much harder to get a consistent understanding of what vibrations cause which activity. So here's our framework for activity recognition with vibration in our farm environment. First, we have redundant sensing. So we want to address the possibility of physical damage from our environment by having very tough, well-protected sensors, and we want to have quite a few of them so that we can have some sensors will back up others. Then we have our per sensor analysis module, which addresses the sensor unreliability because different sensors in different locations might experience different environment-based noise. So then we do our time frequency characterization of load changes, and then a supervised learning for long and short term. And then we have our combined sensor analysis, where we combine what we've learned from these different sensors in order to address the unreliability and failure possibilities that would happen with just one single sensor. And we have several options here. First, we can do an output concatenation of our different sensors, which if we only have a few sensors, or if we're only outputting one or two, like one reading for the whole day, makes a lot of sense. Then the farmers have more information to learn from. So that's what we do with our active periods and growth stage. And then we also have, for our more detailed activity recognition, we do a weighted voting module, and then we also do behavior-informed smoothing to really help with combining those sensors and then smoothing out noise. And then we can get the time the sow is spent laying and then also the time the piglets have spent nursing. So for the first module, we have environment-resistant vibration sensors, where we have IP67 rated boxes to really protect the sensors from the environment, and chemically resistant protected cables as well. We want very simple hardware because then they're cheaper and easier to replicate, so we can have more of them, and they restart quickly when they lose network connection, which happens a lot. By having the option for more sensors, we also can test different types of configurations. We had two different setups for sensors, where the first one we have the sensor inside a protective box so that it will presumably be more protected and last longer, but perhaps have a weaker connection to the structure. And then for setup 2, we put the sensor outside the box, connected with a protected cable. And this we may fail more easily, but also may have a stronger connection to the structure. So for getting this data, we want to characterize what the vibrations that we're seeing. I'll play a video. So you can see that here the sow is laying, and we're getting some fairly small amplitude vibration. And nursing, we can see that there's more happening, both low and high frequency signal. And then when the sow gets up, we see a spike, and standing also causes a lot of movement in the signal. So we can characterize these different changes with time frequency-based features, where we look at how the frequency changes over short time periods, and we can do this with either the wavelet or the short-term Fourier transform. And then, after getting features, we do supervised learning. Our individual sensors are unpredictable. They experience different types of noise based on where they're placed, and they also may be more or less likely to lose connection or fail based on the environment. Like in one case, a pig actually got out of its pen and pulled some of the cables out that were connected to power because we had it protected from the pigs in the pen, but we didn't have everything protected in the hallways. So in order to deal with these different possible noise and failure options, we build a separate classifier for each sensor so that can adapt to different noises based on the different locations and more easily ignore lost sensors. And then we want to combine these classifiers for each sensor. And here we take the confidence score for each sensor's classifier, and we put each confidence score into a simple feed-forward network, which really works a lot like a regression, but with a nonlinear relationship, so that we can better characterize the nonlinear relationships between the sensors, which is caused by these structural differences and varying noise. And then when combining all of these different confidence scores, we output the most likely activity. For example, is the sow laying? Yes, no. Is the sow nursing? Yes, no. And so we have one of these for each activity. And with these output over time, we use pretty small windows, but our activities often last for much longer. For example, nursing may last for 5 or 10 minutes, and laying may last for 2 hours. So we can smooth our signal over time using a consensus-based filter, and where the activity that we're looking for decides how long our smoothing filter is. And then this effectively debounces our data so that we're not switching very quickly between activities. So we deployed our system at Beta Grow Farm in Lopburi, Thailand. We used 3 months of data in 3 different pens for our we used a camera for ground truth, and we had to manually label this data by looking at the camera. So for some of our evaluation, we only use a few days and not 3 whole months, because we have to manually label it. And we detected the sound nursing and lying activity, and then we also detected our piglet growth metric and active periods. And you can see we have a diagram of where all the sensors have placed, and then a picture showing how this looks in the pen. So first we want to evaluate our characterization with time frequency features. And so we used a wavelet transform to characterize our piglet daily metrics. And here you can see that just using the first and second PCA scores just to visualize the data, we can pretty easily see how the different growth weeks of the piglets are separable based on these wavelet features. And then for the sow, laying versus standing, and also for nursing, we use the short-term Fourier transform. The wavelet was equally good, but the short-term Fourier transform was a little bit faster for processing. And we didn't really need the same low-frequency characterization because we use much smaller windows for these daily metrics. And we can see here that there's also reasonable separability with this data. Then for our behavioral smoothing, in our non-linear weighted voting, we can see that our weighted sensor fusion, which is this green bar, shows greater accuracy, and it shows greater accuracy than any one sensor and better accuracy than a majority vote. And then adding the smoothing also increases our accuracy by quite a bit. And these results let us predict birth the day before it happens, 24 hours in advance, because we can the sow stands up and lays down much more often right before she gives birth. She does something called nesting behaviors, and when tested, our recognition algorithm can detect that. Our overall comparison with vision shows that we can achieve competitive results in activity detection. We achieve about the same when it comes to lying, and we achieve slightly better results when it comes to nursing. And this is because, I think, as mentioned earlier, when detecting nursing, the sow is sometimes blocking the piglets in the camera, so it's harder to see them, and also it's sometimes harder to see if the piglets are actually nursing or if they've just fallen asleep next to the sow. Whereas because our vibration sensors detect the motion of nursing, they don't have those problems. Here's just some lessons from our deployment, where here at the bottom is a video of our very first deployment, how terribly it failed. But we learned a lot, and now our third deployment is the one. They last not even a week. So in conclusion, we designed a framework for recognizing piglet and sow activity in a pig pen that handles both environmental damage and time-varying noise. We characterized our different pig activities with changing structural vibration, and we achieved competitive results in detecting lying and nursing behaviors. Thank you very much.